Thank you for the invitation, and thank you for the invitation to the semester, so that I'm able to interact with many of you. Today I'm going to talk about a problem in a setting where the number of dimensions is infinite, so I hope this is high enough for this semester. This is a joint work with Ming-Jun Lai from the University of Georgia, and I studied this work when I was at Georgia Tech, and he was visiting Georgia Tech. This is, okay, Ming-Jun Lai is a professor of applied mathematics, and he recently published a book on bivariate splines at Cambridge University Press, actually. And we thought that it was interesting to use these tools in statistics. And we are supported by the London Mathematical Society. I must say that before giving this talk, I was hesitating between a few topics, and instead of talking about some incremental research that is in press or maybe accepted, I'm talking here about my most rejected papers. It's 5 times already. Last time was yesterday, so you see, it's cutting edge research. So why is it rejected that much? I mean, I know why, because I have reviewers that write about it. But I think there's something novel to it, but it still has to be worked out a bit better than how it is now. We have some examples that will motivate all of this in some theory, sure, but let's look about it. Let's look at the here the outline of my talk. So here, first I will introduce the problem, then summarize the 700 pages of my colleague's book into a few slides, and afterwards introduce the linear functional model and talk about approximation of these of the linear functionals with penalty or not, the case of discrete observation, simulation, and an application to ozone forecasting. So first, what is functional data? So we talk about functional data when the object of statistical study is not just data points, just not numbers or even vectors, but say random curves or surfaces or manifolds. And there are many references now, one of them being the update of Ramsey and Silverman's book, another one being Ferretti and Vieux, another book, recent book on the topic, on regression mainly. As for functional data analysis on surfaces, not on curves, there are not so many published works, and I would say that there's one paper with discussion that was actually published in 1999, but that's about it. Maybe you can correct me if I'm wrong, but that's not something. So here, this is the motivating example, and we're going to go back to that at the end. This is, as you may recognize, the United States. And here we have a polygonal domain. So we simplified a lot the shape of the United States. And as you can tell, there's a triangulation there. Those triangles here, it's not exactly clear, there are triangles over, but there's a triangulation. And here, what is that? It's the spline fitting of measurements across the US taken at 900 or so stations of ozone, ground level ozone.
Make a facetious comment.
Yes.
If you look at it upside down, it looks like a unicorn.
Also like a dog, actually. 2 ears and a snout.
So it's not the United States, that's for sure.
It is not, yes.
Sorry to interrupt.
We simplified a bit Texas and Florida here. Okay, well, whatever. So here's the same spline surface, roughly, but no, without the triangles and only with the locations of the stations. Okay, so you can see the surface here. it's for one measurement, so at 2 p.m. one day, just to motivate all of this. Okay, so what is a functional linear model now? It's a regression model where the response is a real random variable, but the explanatory variable is a random function. So here in our setting, we will talk about a functional linear model with a random surface as a explanatory variable. Okay, so Cardo, Ferrati, and Cerda published 2 papers on the estimation of the function of interest in the functional regression model, and used splines already in 1D setting. Okay. So what is the regression model? Let's be a bit more precise. So here y is a real valued random variable. X is a random variable taking its values in a Hilbert space, H. So here we're going to consider L2 of D, and D is a polygonal domain, the one that you saw before, for example. And y is the integral of g of s, x of s, ds plus a noise. And x, again, is the surface here of interest, and g is the function of interest that we want to estimate. Okay.
Can you relate that to the ozone problem? I'm not so clear which.
That's a very good question. Right now, okay. So say, for example, that you want to predict the outcome in terms of admissions. I don't know that it's in terms of health effect, say. Okay, you have a measure of an health effect, so you can measure at a certain location the health effect as a number. Okay, and you may integrate the surface of ozone to get this health effect. What we did at the end of this talk was here for why we were considering the value of the ozone level at a specific location in the future. Okay, I think it's not the best example because we may want to consider a time series model if we want to do that. Time series of surfaces, that's the best thing to do.
Wouldn't it also be true that in some sense you could think of prediction of a surface given a surface, right? I mean, you can imagine being interested in the effects of health effects of some sort at a number of locations and sort of try to interpolate over the United States.
Actually, there's another motivation. NOAA, I think it's National Oceanographic and Atmospheric Administration in the US, gives a seasonal prediction of weather. Say this summer the weather is going to be rather hot or not in specific regions. So NOAA can provide surfaces of, say, temperature, and this has an impact in terms of pollution levels. And then you may want to regress the weather and get an idea of the pollution level. This is an idea. So the objective is to determine G, and based on observations. Okay. In the 1D setting, there are many published work, as I said. So when the curves in 1D, when the curves are assumed to be fully observed, the principal component analysis for curves was developed. And I can cite here 2 recent papers by Peter All and co-authors in the Annals of Statistics, and they solved the problem of prediction or estimation in terms of optimal rate of convergence. If the curves are not fully observed, there are some other work. So this is an interesting problem in 1D. Here I'm going to work in 2D, so please be nice with me. If you know Peter All, please don't tell him it's an interesting problem, because you might solve the problem much faster than I will. So our goal here is a good approximation in the bivariate setting of the function of interest. And the tool will be bivariate splines. So I will give more details about bivariate splines in a minute. But what is the advantages of using bivariate splines? So it does not require a square domain as wavelets or tensor products of splines do. I've heard that recently some people are working on wavelets that can be defined in non-square or non-rectangular domains. It includes the finite elements. There was a paper by Tim Ramsey in 2002 that addressed this issue, not in a functional setting, but when you have complex domains. It includes the finite elements. It has also the advantage of having an explicit or a more explicit representation compared to thin plate splines. That's a paper on thin plate splines also. So it has many advantages. Another advantage is that the computations are quite straightforward and the programs are working fast. So let's talk about it in more details now. So bivariate splines. So if delta is a triangulation of the polygonal domain of interest, so that is a partition of the domain into triangles, we denote T in bars for each triangle in the triangulation, the longest length of the edges. Rho T, the radius of the inscribed circle in each of these triangles. This describes the shape. This is going to be used in the talk today. Delta within bars is the size of the triangulation, the longest length of the edges. Okay. And this is theta delta is the smallest angle of delta. Actually, the triangulations that I used are usually so-called Delaunay triangulations, where you want to minimize the maximum angle in the triangulation. But then you have to be careful. My colleague and I have tuned the triangulation so that things get better, but it's quite still empirical. Okay. And now, what is the space of splines here? SRD of delta is the space of piecewise polynomial functions over each triangle with smoothness over the whole domain, some specified smoothness. So if you think of the 1D problem, you have knots usually when you consider splines, and you have a degree for a specific polynomial in between, and then some smoothness condition at the knots. Here's the same idea. You have inside each triangle a polynomial of degree d, and then you have conditions across the triangles. Okay. So we make this assumption, which is a technical assumption here, to get some optimal approximation properties. That's not my work, that's my colleague's work in terms of optimal approximation. So Minjun Lai and Larry Schumacher published this result. It's a bit complicated. I don't have time to cover everything, but say there exists actually a spline that approximates any function in L1 with these conditions here when you take the derivatives with respect to the x and y variables. The idea is that in LP norm you can find an upper bound which is related to the function itself in terms of its norm in terms of derivatives and P norm in terms of derivatives, and the size of the triangulation. Okay, so if you take a size of the triangulation that is smaller, then you get a better approximation. Okay. There are many technical details, but yes?
What's delta again? Is that the minimum edge length?
Yes, it's here. No, the longest length of the edges. Now when we have data points at certain locations, so observations zk at locations sk, we have 4 cases here. I mean, this is very empirical again. This is roughly what we can decide according to what we observe. Okay, so say if we have n the number of locations about the same as the number of vertices, that's for case 1. If n is much bigger than the number of vertices, that's case 2. And the last 2 cases actually won't be addressed, but we can talk a bit about them. When n is much bigger, but not, I mean, it's bigger but not much bigger, or it's smaller, when you have less locations than vertices. It's very qualitative because where are those locations? It's an issue, and so on. Actually, we'll talk about that at the end. So case 1, when you have roughly the same number of locations or observation location of measurements and number of vertices. Say we can assume that the number of locations is equal to the number of vertices, and then we can interpolate. So that's the idea here. Mingjun and his colleague proved that the set of splines that actually interpolate at those observation locations with these data points is not empty. So now what is the choice is to find the interpolatory spline here in this set that minimizes its energy functional. Why? Because it has good properties in terms of approximation afterwards. Okay? So this is the energy functional. It's very similar to the 1D case. And then it can be proved that this exists and it's unique, and it has a nice property that, again, if under some technical assumption, the interpolatory spline that minimizes this energy functional is close to F in L infinity norm, again related to the maximum length of the triangulation. Case 2, when you have many more data points than vertices in the triangulation, we may use least square fit, okay, or penalized. So here you want to minimize the sum of squares of the differences between the observations and the value of the function at that point. And you can also introduce a penalty. Actually, penalty in practice seemingly work better. Again, it has been recently proved that this exists and it's unique. It depends on on several quantities. So I won't go into too many details, but the quantities here, the quantities A1 and A2 that I will introduce, are related to the spread of the points, or the location of the measurement location, or the points, relative to the triangulation itself. So see if F is a polynomial of degree D here. A1 is the largest number such that A1 times F in L infinity norm over this specific triangle here in the triangulation is smaller than or equal to the sum of the values of the function inside. Okay, so roughly when A1 is positive, okay, that means that the data sites are evenly distributed over delta. Okay. It's not very clear that it's exactly that, but it's roughly the idea, because if you have too many, if the L infinity norm is too high or this is too small, you get into trouble. It's reasonable to assume that A1 is positive when n is greater than the number of vertices. Now, rho is here stands for the penalty. If you assume that there exist at least 3 data sites that don't lie in the same line, then you can prove the existence of uniqueness of this spline with penalty. Sorry, and it has nice approximation properties. Another quantity of interest is the kind of the opposite. You see the formula is upside down, kind of here. And here it measures, I shouldn't have written this, but the maximum of number of locations per triangle, okay, kind of. If you have too many locations per triangle, this will be very big, and A2 has to be infinite then. So if you assume that A1 is positive and A2 is finite, then you have this nice relationship between F and this spline here in infinity norm, and it's related to the quantities A1 and A2 here, and the maximum size of the triangulation, and it depends on other quantities, the constancy. If you have a penalty, it's exactly the same, almost the same, and here something shows up there. So it's very technical, but it's the same idea. Now the case 3 and 4, again, if you're in a situation where you have more locations than vertices, but not many more, You see, it's more like a discussion here, but not very precise. Or if you have in case for less locations than number of vertices, well, you could use the penalized least square method, but there's some problems here. There are not yet known approximation properties for these splines here, these approximations. And there's even a counterexample in some particular cases where it does not converge to F. Okay, so now let's go back to some statistics. So forget about these bad notations here, but say our functional of interest is g scalar x. So remember this integral over the domain. And we want to solve this minimization problem here. Obviously, the solution is exactly what we want here, but we want to change the minimization over all the functions in H, which is here L2 of D, into this minimization over the spline space, okay? So we want to minimize the expectation of the difference, okay? It turns out that, as in many minimization problems, the problem reduces to solving a linear system, and which is here the system AC equals B, where A is the matrix of size m by m. M is the size of the spline space, and here this is a basis for this space. Okay, this plays the role roughly of a covariance matrix. Okay, in these spaces. Okay, and B is this vector. Okay. So this is not well written, but it mainly says that if you have if you generate enough surfaces such that you only have the zero spline function orthogonal to all the random surfaces that you could generate with X, in that case A is invertible and the minimization problem has a unique solution. And here under some assumption, alpha plays the role of G as before. If you have some assumption on the regularity here, on the smoothness, then it's not very nice. It's quite simple, but it's not very nice, but it's helpful enough for the results afterwards. You see that alpha, the quantity of interest, minus S alpha, this quantity here, sorry, the approximation in the spline space of alpha. The expectation of the scalar product is smaller than a certain value. Okay. We would prefer to have alpha minus S alpha in some norm, it's smaller than something, but we didn't reach that point. And now we can look at empirical estimates. If you have a sequence or a sample of random surfaces, fully observed still, what can you do? Well, you replace the expectation in the minimization problem by the average here. And it turns out that the solution to the minimization problem, again in the spline space here, is the solution to a linear system, I mean through its coefficient in the spline spaces. And this is the matrices of interest for that system, the empirical equivalence to the previous ones. And now this is something that we kind of mimic from the previous literature. Again, if only the zero spline function, or at least with high probability, is perpendicular to the space spanned by the random surfaces in the sample, well, then there exists, I shouldn't have written this, but with a high probability, there exists a unique solution to this minimization problem. So you exhaust the space, kind of. Okay. Now, the convergence in probability of this empirical estimates towards the theoretical estimates when you fully observe everything, we have a sequence of lemmas here. Don't ask me exactly what is a beta quasi-uniform triangulation, but it's a condition of uniformity in the triangulation. It's a bit technical, but here it's a very simple lemma. It looks simple, but it's not that simple to prove. But I should have put the L2 norm here. So when you have a spline, you can relate the L2 norm to the calligraphic L2 or the small L2 norm of the coefficient, the sum of squares of the coefficient. Okay. So this is another lemma that is used here, obvious for obvious reasons. When you have two systems and here two linear systems, and the matrices and the vector of interest here are very close, then the solutions have to be close. This is standard linear algebra. It depends on some other quantities. So when you have here the difference between the entries of the matrix in the theoretical case or population case and the empirical equivalent here, A n hat and B n hat very close, then you should have the solutions to those systems very close. So exactly, I can skip that because it's not very important, but in our case, we use the Aufdiening exponential inequality, which is a standard results for independent random variables. Why? Because if we assume that we have a sequence of random surfaces that are ID and bounded, this is quite a strong assumption. If we assume that the noise is also bounded, we will not use this assumption later, but just here. Everything is bounded. Linear function of them bounded, that's fine. Then the empirical estimates converges to the population estimate in probability with this convergence rate. Okay, so that was a criticism by the reviewers because M is the dimension of the spline space. So sure, if you have more and more data points, you should this should change also according to the sample size, but at least we have some bound in terms of the difference between those two. Okay, but under some conditions like this, we can get a convergence rate, for example. Now I would like to thank Vladimir. When I was last year talking to you with my colleague, just a little trick about when you have a Gaussian noise, that you can use this little trick. And then you can apply the same machinery to the case where epsilon is a Gaussian noise, and then you have the same, roughly the same type of convergence. Now if you have a penalty, and you want to solve this problem with penalty, the choice of penalty is a problem, sure, for the parameter here. What is this notation for? It denotes the semi-norm of the empirical kind of semi-norm of this. I mean, it's not the empirical, but it's the semi-norm of beta up to R. So that's the notation. Here you have the partial derivatives up to some order. Again, since the spline space can be dense in L2, we consider the spline space over a certain triangulation with delta sufficiently small. One of the asymptotic is with delta sufficiently small. In practice, it's difficult to have more and more triangles, but that's the idea of the asymptotic here. So again, we look for an approximation. Here we replace the argument minimum over everything with the argument minimum over only the spline space. And we hope that we have a good approximation. Indeed, when you solve this problem, you again fall in this case where you have a linear system. And the matrix A compared to before is just exactly the same, but you have something of a penalty here. The penalty comes into place, and the penalty is based on this ER, this expression, but taken at those spline functions. And again, we have the same results, so I'm repeating myself, on the minimization problem and the existence of a solution. And another technical result enables us to, again, find an upper bound for the expectation of the scalar product square. Here you have the difference of interest, the alpha minus S alpha rho. And when you have empirical estimates, it's exactly the same machinery. You take the argument minimum of the average instead of the expectation, and you solve a linear system with the empirical estimates and not the original matrices and vectors for the system. Same result as before, so it works again when you have a penalty. And here, same results. I didn't put the rates of convergence, quote unquote, but you have convergence in probability of the estimates towards the real quantity here. I mean the quantity S alpha rho. Same thing here when the noise is Gaussian. Now, when you have discrete observations, so this is all based on fully observed, a sample of fully observed surfaces. But it's obvious that in practice you have observations over some design points, as I showed in the motivation at the beginning. We have to replace X, the surface that is supposed to be fully observed, by some approximation. And actually, we're going to take the spline approximation of this surface. It makes sense as well. So we solve the same minimization problem, but we replaced X by Sx here. Okay. So this is the functional plus the noise, and we do this. Again, we replace the space by the space of spline here as well. And under some assumption, we can prove, again, the same type of result. But what is important is that we can carry on as well. We can continue to look at empirical estimates based on discrete observations and spline approximation of the discrete observations to find a solution to this problem. And we solve the following system here, the following matrices here, where everything has to be approximated. But everything here is easy to compute because all the scalar products are in this computed using spline, bivariate splines. So there are some nice algorithms for that. So it's fast. And we have some differences here, but it's the same story as we approximate better the discrete observations by their spline approximation, then we can establish the convergence of the empirical estimates toward the other one. I shouldn't have written that because then it should be S directly here. But in 2 steps we get to the end result. So here let's look at the same domain, okay? But let's carry out a simulation on the domain. Okay, so this is a realistic domain. It's not perfect. It's a polygonal domain of the United States. We actually considered 2 triangulations. The problem of using the best triangulation or the optimal number of triangles is a very difficult problem. We don't have, we just investigated this problem. It's not even in the paper, but you know, how many triangles should you consider? And you see the problem here is that in some areas where there's not so much population, such as say the Dakotas or Montana, there's not so many. There are not so many observations, whereas on the coast there are many. Actually, on the coast it's very difficult. Here we missed a few. It's very difficult because you cannot borrow strength across the ocean, so it's more difficult to approximate. Actually, when we did some other numerical experiments, it's usually on the size that you have the most, that is the most difficult to estimate the function of interest, I mean the regressor. So here, this is the functional model, so Gx, and G is this function. We took a sinusoid over this domain. We used S15, so again, this satisfies the initial property that I talked about at the beginning between the degree of smoothness and the polynomial, the degree of the polynomials. We used this was optimized by hand, really. We could have done cross-validation, but we didn't. And there are 969 stations, and we generated random surfaces. So there are many ways to do that, but I don't want to go into too much details here. But we tossed a random series of coefficients in the spline basis, and then we added some noise. So we generated random surfaces X as a pseudo sample for our simulations. Okay, and so that therefore we could compute the exact value of the yi's, and the goal is to estimate alpha, and then we add the noise at the end. So I said here that the small sample properties are good. Well, what does it mean? It means that after looking at this table, sorry, it's very small. I should have made it larger. But you see, when the sample size is only 5 surfaces or 20 surfaces, this is the empirical L2 errors for the differences between the estimate and the real value. You see the values are quite large, but as soon as you get to 100 or 200 for the sample size, then you get to L2 errors that seemingly are much smaller. And we did we did 20, not many, but 20 Monte Carlo simulations on 20 computers at the same time, because all of this takes some time. And here, this is the L infinity, empirical L infinity error, so the supremum of the differences. This is a bit more difficult to assess because you can have a spike at some location and therefore run into problems. But here you see that, again, roughly maybe 100 for the sample size is enough to have very good approximation properties. And now a real example. So instead of doing a simulation on this particular domain, maybe I should go back to the beginning and show. Oops. Yeah. If I do this, show the motivation here. So what we did is we considered a specific station in Atlanta, and we tried to predict for the day after at the same time, using the surface from the day before at the same time, the value of the ozone concentration at that particular location. Okay, so the Y was the value of ozone the next day at this particular location. Okay, using the regressing on the whole surface. Okay. So now if I go back to one of these. Okay. So here we put 1 week learning, which means we used only 1 week to construct our estimator and predict. Using this estimate, it was not that bad. It looks good because also we capture natural variation during the day, but it's not that bad. It's time, sorry, it's the 24 hours. So we did it repeatedly, that's a good question. We did it repeatedly for each time. So for, say, 1 a.m., we used the 1 a.m. surface the day before, and we predict the next day using that. Okay. 10 days learning. It's not the same day, obviously, but we using 10 days. You see, we missed many points here, and also we made predictions that are negative. It's not true that the ozone concentration can be negative. So it looks okay, but there's still a lot to do here, and we have to compare. We didn't do it. We have to compare with other methods.
So 10-day learning means you took the 10 1 a.m.s previously.
Yeah. Yes.
Use their average to.
No, we build the estimate of the function in the regression that of interest. We build that based on the sample size of 10 days. N is equal to 10, the middle n. So It's very, we should use more days, obviously. But it's just an attempt to see if it works, and it does. It's also maybe not the right idea, because in prediction versus in estimation, you may want to use different estimates.
How do you justify your IID assumption on this kind of data? I mean, it has been the case that for function data, it always is IID.
Mm-hmm.
And so there's a general, there's a basic question whether function methods can be applied to this type of data at all.
Yes, no, it's very good.
It's rather the time series aspects are more important. For example, here maybe it's not even stationary.
Yeah, no.
The system may not be even stationary. Not to speak of independent, but not even stationary perhaps.
Yes, there might be a trend. For example, over the weekends, it's a different story also. So you have different means, and you're totally right. There's a dependence, obviously.
I mean, there is some functional time series methodology,
Yes.
right? There are several people in France who have done this.
Actually, I've written a paper on that problem with time series of functional data to predict ozone, the autoregressive model regression.
Yeah.
So then you take it fully into account hopefully fully.
You mean it's a functional autoregressive?
Exactly. That's what I did actually in the same kind of example. But we're working with Mingjun on the extension of that to a time series of of surfaces. Yes, it's a bit tricky, but we should get to a result. But for that particular example, you're totally right. That's the way to go.
What we found with ozone, at least at a daily level, is that if you take a functional autoregressive approach, then those innovations you can treat as independent. That's sort of an AR1 in terms of days. So you can sort of get back to that independence assumption by looking at the increments of regression.
We didn't do it yet. We did. We're happy already that we could get something, but that's maybe not the right example to look at. Therefore, it should be maybe a sample of. I know that you're working on many biological examples where you have maybe truly ID sample and of.
The dependency is certainly an important question, and one wants to extend the method in a wide way to dimension dependencies. So
Yes.
it's just that, of course, for IID, it's easier to do a theoretic development.
Exactly.
And also dependencies more complex, like what kind of dependencies you have, and so on and so forth.
Yes. Good point. So now, what is work in progress? So actually, you see, it is a mistake here. It's autoregressive time series. So we're working on the extension where you have time series of surfaces. And one of the motivation is actually the seabed prediction or bathymetry. At UCL, we have a department of it's called civil engineering and geometric engineering, where people measure the depth of the ocean near the coast, and they try to use numerical models to predict the future depth for the next decades. They say that more than 6 months it's very difficult. So you have obviously a surface. You want to predict the surface for the next decade under the forcings of climate change, and statistical methods here are welcome because there's no real. It's very difficult to model this. Hopefully, nicely they have measurements back to the 19th century, so every decade or so. So we have time series again of surfaces, and they're clearly dependent because the seabed evolves across time with dependence. And that's a clear motivation. Actually, one PhD student already worked on that with profiles in Wendy, and it worked already better than the methods that were used previously. So we hopefully we will be able to do that and include forcings. So the if you have climate change and you have more and more storms, then the seabed will evolve accordingly. So that's nice forcing. Right now, we're almost finished with this work where we look at L2 convergence, not convergence in probability, but a stronger mode of convergence with more assumptions, but we have a better mode of convergence that's more theoretical. We may want to go for a nonlinear functional regression where maybe on some it's partially linear or locally linear. And now something that that's a recent motivation of mine. So for this ozone problem, it's not like for the seabed. You have numerical models, chemistry transport models, that can predict for the next day the level of ozone across, say, the US. Okay? But there are many parameters in those models that are not really well known. Some are fudge parameters, some are parameters that are linked to physical quantities, but they're not really well known. So there's a lot of work right now on calibration of computer models using comparing observations with the runs of the models and running the model with different set of parameters and finding the best tuning parameters for this model. Okay? And recently there are two papers that came out by Susie Barry, Jim Berger, and collaborators on functional calibration, where they use wavelets to actually compare the or describe the model outputs and compare that with the observations and do the calibration directly on the coefficients themselves. It turned out that it works better than just a raw calibration with data points that are not functional. And also Dave Ingdon at Los Alamos and a collaborator did not the same, but a similar analysis recently. I don't know if it's published, maybe it's published now. So here, the idea would be to calibrate the computer model that gives the prediction of the whole surface. Actually, it provides the prediction of the whole surface versus the observation. So maybe a way to compare those two and to therefore improve the numerical model would be to describe the both surfaces in terms of coefficient in the splines basis, and then calibrate directly on the coefficients. So that's an endeavor that for the future, but right now I'm doing calibration of this model directly on some locations. It's working, but it's not yet I think the ultimate goal, which is to include more spatial information. And this is the end of my talk. Thank you.
Is there anything to be gained by taking logs of the ozone data?
Yes, that's true. Yes, logs or square root, I mean, depending on. Yes, 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 and the variability. People do that, yes, often. Yes, that's true.
It's kind of fitting, but the bivariate splines use it all in, say, computer models in industry.
That's a good question. I don't think so.
The models are usually these surfaces, these Gaussian surfaces.
Yeah. In industry.
Well, I mean,
or
really, I mean, I guess I'm just influenced by the fact that I was at this conference that Jeff Wu organized, a whole session on computer models, which I thought was very interesting. And there was all these sort of random effects kinds of models, which are telling yourself a story that you have a realization of a Gaussian process with a spatial covariance structure.
Actually, here I'm not addressing at all the spatial covariance structure, as you noticed. But I haven't seen that. No, I haven't. I don't know.
Well, if you're doing regularization, you're equivalently assuming a Gaussian structure. If you're assuming a particular covariance for a Bayesian problem, whether you want to, sort of go that way or not. is your choice. But
Yeah.
the regularization fixes that.
Mm-hmm.
So like that second derivative squared
Sure.
integrated penalty, that's sort of saying something about it being looking sort of like a limit of a Matern covariance. as
Uh-huh.
arranged as
So there's a strong relationship here. Is there any reference for that particular? No.
You know, Grace Waba talks about it, but
Uh-huh.
that's, you know, it's Grace Waba, so it's as clear as she writes.
So in these examples that I've heard, they were not taking limits in any way. They were not regular. They were not using them to regularize. They were actually fitting these models. They're fitting the coefficients of the return covariances.
Yeah. Well, that's when you're actually fitting the covariances the Matern, it's sort of like you have all these different regularization parameters that you're estimating using maximum likelihood.
Mm-hmm.
Method. You still have the regularization there. It's just these tuning parameters you're filling in. Serge, you said something. If this is a long answer, we can just talk over lunch. But you initially, when you were talking about the triangularization approach and filling that in with patches of polynomials, you said this has an explicit form as opposed to, and I think you were referring to the radial basis function representation.
Thin space lines, yeah.
I didn't follow that because I didn't see anything more explicit. Were you talking about theoretical results or?
Okay, explicit. Here you have a description of a spline in terms of its coefficient in the spline spaces, bivariate spline spaces. We have an explicit basis. Actually, the dimension is I mean, I didn't write it down, but you can explicitly construct a spline basis, and
okay.
the dimension I don't remember by heart, but it's related to all the other parameters. Okay.
Okay.
For thin space lines, I don't see an explicit representation. Maybe in a, I don't know. I mean, do you use this thin space lines? No.
Yeah,
I've used that.
Yeah, and clearly we have R programs that fit it,
Yes.
so it has to have something.
It has something. It fits it, but what about the explicit representation in a basis? Do you have a basis? And
Yeah.
yeah, we have a basis. I mean, it's radial.
Yeah, there's a basis. You may not like it, but you know, but I can tell you about it.
Okay. You know, I'm very interested. The problem is that it's radial, you know, also.
Yes.
So you go, but do you go in each direction? I mean, is it quite isotropic or? Yeah, it is.
Yeah.
Okay, so that's another issue maybe. That. Mm-hmm. But it's still quite attractive. And, it works. Good.